Hello everyone, and this is the Ganesh. Welcome to the video on design of IIR filter of digital signal processing. This is the problem given to my students. The IIR filter specifications are given below. Passband age frequency is 2 into his or her roll number. Stop band frequency is 3 times of their roll number in hertz. Sampling frequency is 10 times of roll number. Passband ripple is zero point 0.8 plus roll number divided by 1000. Stop band gain attenuation is zero point 0.1 plus roll number divided by 1000. Zero point 0.1 plus roll number divided by 1000. Sampling time is 1 second. We have to use impulse invariance method into this, and I ask you them to calculate the order and the cutoff frequency manually, so that they can verify these results on the in the MATLAB programming. Design the IR filter using the MATLAB programming with the magnitude and phase frequency response, and test the filter response with the test signal. This is the test signal here, where this is the fundamental signal, this is the fifth harmonic signal, and this is the seventh harmonic signal with amplitude 10, 4, and 2 respectively. So let's see how we can design this filter. This time I'm going to use the MATLAB live editor so that it is easy to understand. So you can create here a live script. Okay, so if I create a live script, already I have created one live script for IIR filter. So in this live script, I'm going to see the design of filter. So I will put this. First, do the some settings into this. You go in the view mode, click output on the right side mode. So every time you will get the output on the right side mode. Okay, so first I will give the title here. It is a design of IIR filter. Then uh, program by. Okay, so this is the program which I'm doing this program. So wait a minute, so that I will increase the font size so that it will be readable to you. So let's check whether it is possible to change the fonts of this command window, command history, editor. So for editor already I have set the 8 font size, 18 font size, but I think in a script editor the font size is not editable. So let's create a full screen. Now this is the program. So first we will clear all and CLC. First I will do this clear all and CLC. Then uh, let us write down what are the specifications given. Uh, so before the clear workspace, I have already typed in this program, so I'm copying here. So these are the specifications which are given to me. So for a time being, I will take the pass band age frequency as the 100 hertz. The stop band frequency is 300 hertz. Sampling frequency, I will take it as a 1000 hertz for the sample program. I will take passband ripple is equal to zero point 0.8 and stop band attenuation is zero point 0.1. Sampling time is 1 second, so it is a clear all and CLC. So, okay, so let me check whether I can change this font size. Okay, I think the font size is not editable in the live editor. Okay, so no worry. So these are the specifications given. Now, what I have to do, I have to give the input data. So whatever the input data, so I will give that input data here. I will create a section break and I will give the title here, input data. So what are the input data I am going to give? I am to give the filter specification as the input data. So filter specifications, what filter specifications I need? I need the passband frequency as the 300 hertz, stop band frequency as the 100 hertz, sampling frequency as the 1000 hertz. Okay. So from this we will calculate omega p and omega s. Omega p is equal to 2 pi fp upon f sampling, and ws is equal to 2 pi fs upon f sampling. So this will give the input data in terms of so sorry, I have to create a section break here. So this will give the input data in terms of uh, angular frequencies. Then we'll give the ripples. So point at ripple, pass band gate point at ripples, where and stop band gain is zero point 0.1 ripple. Okay, stop band attenuation is a zero point 0.1. So these are the given specifications. So this converts your sampling frequency, which is in hertz, into it. So let's run this section and see the results. So it will display the results on right hand side. Okay, so first time it will take a time to come the results. Okay, so it is running. Yes, see, this result is visible in on the right hand side. Fp, omega p, omega s is calculated. No, everything is calculated. Now, what is the next step? We have to determine in IR filter design. First, we have to design the analog filter. So first, it is necessary to determine the analog frequency quantities. So let's create one more section here. And now I want to determine the analog quantities using impulse invariance method. So let us see how we can design using impulse invariance method. Okay, so solution t is equal to 1 second. Here we have to calculate analog frequency using impulse invariance method. Analog frequency omega p is the digital frequency. From omega p, how to calculate the ohm p, that is omega p upon t, and ohm s is equal to omega s upon t. If impulse invariance is replaced by bilinear transformation, then the formula will be 2 by t tan of um, omega p. So okay, that is the different omega p by 2. So that is a different formula which can be used using the bilinear transformation. But here we are using the impulse invariance method. Now we have to find out the Butterworth filter. So here I have implemented 1 by 2 log of 1 by as square minus 1 upon 1 by ap square minus 1 divided by log of ohm s upon ohm p formula. So this will give you the n. So we have to design cell function. What is the cell function? Suppose your result is 1.1, it will give you the next value towards the infinity, that is n is the next integer. So 1.1 will be recorded as a 2, so value of the n is equal to 2. So I will show you on what is the cell function here. So if I give the data cell, so cell is equal to 1.1, then it will give the result 2. Okay, suppose if I give you the cell 1.9, then also the result is 2. That means it is rounding up the digit towards the infinity. Okay, so suppose I have given the data cell even 1.05 also, then also it will give the result 2. So this is the function of cell. So that I use the cell function. And how to calculate the cutoff frequency? Cutoff frequency is equal to ohm s upon 1 by as square minus 1 raised to 1 upon 2n. So where 2n is the order of the filter. So from this you will get the order of the filter. Now we'll normalize the frequency. Okay, so here need not to normalize the frequency because already ohm p and ohm s we have normalized. Omega p and omega s we have normalized. So by using the butter command, we can determine the filter coefficient. So numerator comma denominator butter nth order filter with the cutoff frequency of ohm c, low pass filter, which is designed by using the S domain. So here am writing the S. Then we'll type the transfer function hs. Hs is equal to tf num comma den. So it will give you the transfer function of the analog domain. So okay, just a minute. I think in typing, where did I any mistake? Okay, no, n must be integer. So here I have to give the absolute value of, okay, so absolute value, because n should be the positive integer, order should not be negative. So you can see here, this is give the second order transfer function of Butterworth IIR filter. So now we have to convert this filter into the digital filter. So let's see how we can convert this into the digital filter. So to convert this into digital filter, we have to use the different command. So let's see. Again, I'm creating the section over here. So this MLX, that is the live editor, is very useful to see the output section wise. So I want Z in terms of Z transform. So num Z den Z, I'm going to use impulse invariance method with numerator and denominator calculated from the analog filter. So impulse invariance num comma den with the sampling frequency of 1 by t. Now we want to display the transfer function in terms of Z domain. So the command is tf num z den z comma t. So with respect with sampling time t, it will display is a sampling time t is equal to 1 second is given here. So let's run again the digital filter. So it gives you the digital filter design. Okay, so you can see this is a digital filter. It is designed with sampling time of 1 second. So this is the h of s and this is the equivalent h of z of the digital filter. After getting this, we have to determine the frequency response of the filter. So how we can determine the frequency response of the filter? Let's see. And we want to plot the frequency response also. So again, I am creating the section break. So frequency response. So we want to determine value of h with respect to frequency. So for frequency response, there is a simple command in the MATLAB. Use a z frequency response in the z domain. So num z comma den z, which are the coefficients of the numerator and denominator calculated in the line number 33. With 1024 is the sample size of that with f sample. So I have given the f samples data. F sample is given in the problem as the 1000 hertz here. So I'm using that f sample data. Then we will calculate the magnitude of this. So magnitude of h is calculated as absolute value of h. We will create a subplot 2 comma 1 2 rows 1 column, and first plot is f 20 log of 10 h magnitude, line width of 2 and color is a red. We'll give that y label as mod of h of slash omega. We will, it is the latex command, so it will directly convert that latex slash omega into the symbol of omega, Greek symbol of omega. Then grid on, then subplot 2, then we'll plot angle plot. So h angle plot, so plot f comma h angle, line width 2, color red, then angle of h of omega, and on the x label we'll give the frequency in hertz. So you can type the x label here also as frequency in hertz, or you can write on the bottom side also. So if I run this command, so let's see how it will give the appearing the results. See, for, you can see, observe here, this is my low pass filter design. So up to this signals are passed, and from this signals are blocked. Okay, so this is the magnitude response and this is the angle response. You can see the x label and y label. Okay, so now we design our filter, low pass filter. We have to, that means it should pass the frequency signal up to below this, and after that it should be cut off. Now but we want to test this with the test signal. So let us test the our results with the test signal. So first we have to generate the test signal. So how we can generate the test signal? Let's see example with the test signal and how to plot that example with the test signal. Okay, so again I will create the section break. So let's see this code. Example with input signal. So fs is given as 1000, which was there. So t is equal to 1 upon fs. So time is 1 upon fs. We'll create the length of our input signal is 200. So you can take any signal. So you can 200, you can take 300, 400, anything. How many points you need, depending upon that you can take a length. So time vector is creating from 0 to L minus 1 with the sampling time t. So t will be start from 0 to 1 by fs up to the sampling time t. Then test signal I will create 10 sine 2 pi 50t. This is the fundamental one. Then I want this signal as a 4 sine fifth harmonics. So fifth harmonic signal is 2 pi into 250t, that is a 5 into 50. And the next signal I want to create as the 2 sine 7 pi t, or you 7 2 pi t, or you can say 7 into 350t, 7 into 50, that is a 350t. then the input length L is equal to the length of the test signal. So X is equal to FFT of the test signal. This FFT must be divided by the L, that is the length of the filter, length of the test signal. So this P2 and P1 will assign it from, this is a two-sided signal, so we want to convert it into the one-sided signal. So in one-sided, to convert into one-sided is 1 colon L by 2 plus 1. So this will create from 1 to L by 2. So this P1 signal is from 2 to n minus 1 is equal to 2 into P1 to 2 to n minus 1. 2 is multiplied to get the fundamental value. So how to calculate the F? F is equal to Fs into 0 colon L by 2 up to L. So this is the what, just for displaying the result. So figure, then we have subplot 2 comma 1. So first we'll plot the test signal with respect to time. So original test signal time seconds, so there is test signal which is here, it is with respect to time, it is plotted, and its frequency spectrum, yeah, that is frequency spectrum is P1, it is recorded into the P1 signal. So that frequency spectrum is also plotted with respect to the F, that is a frequency signal. So and after that, later on we'll see the filter result. Okay, so let us run this much code. Okay, so let's create a semicolon here, otherwise it will display the results. Again, I will run it. Just a minute, it is running. Okay, so this live editor is very good to observe. So total length is 200. So you can see my signal is having harmonics. Fundamental fifth and seventh harmonics is in the signal. So fundamental, that is 50 hertz signal is of amplitude 10. 250 hertz signal is of amplitude 4, and seventh harmonic signal, that is 350 hertz signal, is of amplitude 2. Now this must be filtered out using our low pass filter. So let us see how full low pass filter will work for this. So I will create another section here, and I will apply whatever my filter design to get the filtered signal. So let us apply it on the filtered signal. So filtered signal is equal to, will filter the signal, that is num z and den z is having the transfer function. So in the num z and den z I am putting the test signal. So test signal will be multiplied with the filter and it is recorded into the filter signal. Then we will calculate the FFT as the same code you can copy, which is here. So same code is there. Only change is what we are plotting the signal, test signal of instead of test signal, here we are plotting the test signal, here we are plotting the filter signal, and the frequency spectrum of the filter signal, that is a P1 we are plotting here. Now let's run this code. Okay, you can run section wise also. So see, here we have the amplitude 10. Okay, so this fifth harmonics and seventh harmonics, you observe that the signal is the most sinusoidal signal, but amplitude is reduced. But other signals, that is fifth harmonic signal and seventh harmonic signal, is almost vanished. Okay, so let us design the filter with another frequency. Instead of 300, I will take it as a 500. I will take it as a okay. Pass band gain is a 500, and I will take this as the 1500, and I will change the sampling time is to 15,000. Sorry, 500. Okay, so I will take it to 1000 and I will create the sampling time of 2000 hertz. So let us do for this results. Let's see how this will give you the result. Okay, so you can see here order of this is 4, cutoff frequency is calculated. So for the fourth order, you can see the signal up to 500 hertz signal is passed with the zero 0.9 attenuation. And if we see here, the fifth harmonic is not reduced, but the seventh harmonic is reduced because cutoff frequency we have kept it as a 500 hertz. So 250 hertz signal is not passed through that. Is passed through that as a low pass signal because stop band frequency, pass band gain frequency is the 500 hertz. Okay, so likewise you can design your own filter with the required frequency. Hope you will understand this video, and